Hello, everyone. Thank you very much for joining us today in the webinar, the Internet of Unmanned Systems using robot operating system. We are very happy to welcome you to the second webinar with Professor Anis Koubaa. Today, Professor Anis, he will talk about, he will give an overview of the emerging field of cloud robotics with particular focus on integration of drones over the internet. He will also present the concept of Internet of Drones and discuss the current state of the art and the main challenges towards its realization and its applications. You will get the chance to learn more about the different solutions and how to integrate drones into the IoT and the cloud, which called the Dronemap Planner, which is cloud-based management system that allows the control and the monitoring of drones / robotics through the internet. In fact, we got lots of very positive feedback from our last webinar 2 weeks ago, and it's really very exciting today to listen to Professor Anis today also. So, Professor Anis, are you online? Professor Anis, can you hear me? I will call him to check if we are in the same Zoom channel.
الو الو السلام عليكم دكتور. دكتور ابراهيم, are you hearing me?
Oh, sorry, I hear you now. I just muted my mic.
Okay, yes. That's good.
Okay, thank you very much for joining us, Professor Anis, today. And I introduced you a few minutes ago, and I mean the stage is yours.
Okay, thank you very much. Just give me 1 minute to
Okay.
fix my microphone.
So as I mentioned a few minutes ago, that we got very good feedback from our PhD students and our master students. The last webinar was really exciting, and it was very, very educative and very useful. We have many PhDs and many master students who are interested in autonomous systems and robotic operating system. So it was very inspiring last time, and this time also we have 50 participants, and the number is increasing as well. First we will have around 1 hour presentations or 45 minutes presentation by Professor Anis, and after that we will take some questions and answers. So we have 55 attendee from all over the world, in fact, which is really exciting. Okay, Professor Anisi has just small problems in his Zoom, so he is restarting his computer. So sorry for this. So in fact, in Olesund, we are one department from one faculty from NTNU. We are located in Olesund, and we have a master program in simulation and visualization, and it's international master program. It is only of its type in Norway and Scandinavia. And we do our best to attract many international students in our master program. So in fact, feel free if you have any questions later on, or if you can just contact me by email, for example, if you need to get more information about our study programs in Olesund.
Okay, Dr. Ibrahim, I think I'm ready now.
Okay. So thank you very much, Professor Anis, and the stage is yours. Thank you.
Okay, thank you. Just make sure that you are hearing very well.
Yeah, it's very well, very clear. I will stop sharing my screen and I will mute my mic.
Okay. Okay, Bismillah ar-Rahman ar-Rahim. Wassalatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Thank you everyone for being here. I'm very excited to give a second webinar. And this time will be about the integration of unmanned systems that are using ROS with the internet. In the previous talk, I have already presented some of the activities around this area, and today I'm going to provide this topic in more detail because we have been working on this actually since a long time ago, maybe around 5 to 6 years. And now we have pretty much some mature system that I will be glad to demonstrate and show in details, both from like a conceptual perspective and also from implementation perspective. So about today, I'm going to present why do we need unmanned system to be monitored and controlled through the internet. I'm going to provide a brief motivation around the topic, and then I will present what are the existing approaches that has been implemented to develop unmanned systems through the internet. And then I will present the conceptual design of, or the ROS lead protocol. This is a protocol that we have developed for the purpose. And finally, I'm going to end up with demonstrations, both using simulated robots and the real robot. So by the end of the lecture, inshallah, you will be able to teleoperate my robot that is here in Saudi Arabia, probably wherever you are. So I will show you the steps, and then you can register into the system and make some manipulation using the system that you have implemented on the robot that I have now in my office. Okay, so what is the motivation? Actually, this has started a long time ago when I has been working with ROS on some developing a service robot. And I already presented the demonstration the last presentation. And if you remember, I was mentioning that the issue is that when you work with ROS, you are confined to a small area, that is your local area network. If you are working around a Wi-Fi router, so maybe you have maybe 10 meters, 20 meters, 30 meters within an indoor environment, which is actually very limited. Of course, you can use Wi-Fi extenders, you can use some different techniques, but still it has limitations, especially if the environment is very large, and especially if you want to monitor your robot from everywhere and every time. And this is actually very common because now most of the robots that are being proposed, they are standalone systems. I mean, you have to use them like point to point, you have to be close to them with maybe some extensions to be integrated into the internet. But there is a need actually for a more comprehensive framework or kind of standard to be able to connect the robots over the internet wherever they are. And not only robots, also for the drones. Okay, now if you look at the drones, the current usage of the drone is that you take a drone and you will teleoperate it with a remote control, and you have to be within a certain communication range. Maybe this communication range would be 300 meters, 400 meters, or maybe 1 kilometer. In some drone platforms, you can reach 7 kilometers like with the DJI, but still you will be limited. I mean, if you want to control a drone in another country, so these kind of techniques will surely be limited. So that's the idea, is actually to leverage the use of the concept of cloud robotics that we'll be introducing later to be able to monitor and control the drones and robots, and in general, any unmanned system through the internet. So the robot and drone will be like wireless sensors that will be mobile, and they will have internet connectivity. And of course, here's the specific thing that we are going to apply this concept on ROS-enabled robots. So the objective is how we can extend ROS in order to make it reachable through the internet. Okay, yes, so this is, for example, if you work in a large environment, this is the map of the College of Computer Science in Building 101 in Prince Sultan University, which we have built with the robot. Yes?
You are not sharing the screen.
Oh. I did not. Is it fine like this?
Yeah, no, it works.
Okay, sorry for this. Okay, so yeah, now the objective is, as I mentioned, to be able to extend the reachability of the robot to regardless of the communication range of local networks. So this take us actually to the concept of cloud robotics, which has emerged since 2010. Okay, so here, cloud robotics, it means we can use robot through the cloud. And to simplify things, there are two possible usages of robots through the cloud. We can use them okay, as a virtualized robotic system. And by this, I mean we can have a seamless access to the robot through services, service interfaces. It can be web services like REST API or SOAP APIs, or service-oriented architecture, or for example, using serialized messages in JSON or XML, something like this. This is what we call virtualization of robotic system. Instead of using like a physical robotic system, like point-to-point, you will use it through some software service interfaces, okay, to virtualize the access. Like we do virtualization now, for example, for the operating system, for the networking. You are hearing about software-defined networking or network virtualization, operating system virtualization. Also, we can do robotic system or unmanned system virtualization as well. And the second important thing is computation offloading. What does it mean? It means that we are going to migrate extensive computation from the unmanned system to the cloud. For example, imagine that you have a deep learning application that you would like to run on a robot or a drone. So in this case, you can use the GPU on board. And of course, this will consume much more energy than if you use a CPU, because deep learning applications are very hungry in terms of energy and resources. And this actually will vanish the energy of the robot quite quickly, especially that the robot operates on battery. And one of the objectives is actually to extend the lifetime of the robot operation. So another technique would be actually, instead of locally computing extensive applications on board, we can migrate them to the cloud, and we leverage the cloud resources to take benefit from high processing capabilities, large storing capabilities, and there is also more resources in terms of energy. Of course, this is a very important topic. There are a lot of research now around computation offloading, and the problem is not as simple as I'm saying now, because even now, if you offload computation, it means you are going to make more communication between the cloud and the robot, and this in itself will consume energy. So what kind of trade-off we need to do to optimize the energy consumption as if we process locally or we migrate the computation to the cloud? This is a very hot topic nowadays that being investigated by the scientific research community. Okay, if you want to have an overview about cloud robotics and software-oriented computing, robotic computing, I have a very recent book chapter in the Encyclopedia of Robotics that is going to appear soon by Springer. Okay, so in our work, we have started to make virtualization of robotic system through using the ROS link, and then also we developed some initial prototype of computation offloading I'm going to show in the next slide. One of the milestones in cloud robotics, which I consider, there is the European project Robot Earth, okay, which have developed a complete ecosystem for the collaboration of robot through the cloud. So they actually developed a Robot Earth database, which contains shared knowledge among the robot that they can use in order to perform some mission tasks in collaboration. This project now is one of the most important in the area of cloud robotics in the area of computation offloading. On the other side, in what concerns robot virtualization or allowing to access the robot through web interfaces, there is the ROS bridge suite, which allows actually to serialize ROS messages into JSON and send them through a WebSocket. This approach is very interesting, but for the context that we wanted to work with, as making the robot connected through the internet, there is one limitation that was faced, that the ROS bridge server is located inside the robot, okay? So the server here is located inside the robot. It means the robot needs to have a public IP address to be reachable through the internet. And this is something not very like trivial, because usually the robots work in private networks, and maybe they don't necessarily have public IP addresses. There are some techniques in networking, like using network address translation or kind of firewalls, stuff like this, to allow the access. But you know, it is not straightforward. I mean, you need to make some kind of mechanics into the network to make it work. And you wanted something more smooth and more natural. Okay, so for this reason, we wanted to develop our architecture, which consists on, let's say, moving ROS to the cloud. And the objective is to be able to make computation offloading of extensive applications to the cloud, and also to virtualize the access of the robot through web interfaces. So these are our two objectives. The ROS bridge here was mostly dedicated to virtual access, and the Robot Earth was dedicated more to the computation offloading. And here in our approach, we wanted something more unified to allow both cloud robotic strategies, that is virtualization and computation offloading. And we wanted to leverage the use of cloud computing and IoT resources to do so. So I would say that I have been much inspired by the MAVLink protocol. So people working on unmanned aerial systems, they know well about this protocol. It's the gold standard for the communication between unmanned systems. And you can see, for example, you can have a drone at the ground station, and here they will exchange some kind of messages, Mavlink messages. For example, they can tell about the current location of the drone, the GPS location, or the altitude, or the linear velocity, and the angular velocity, and so on, the heading, and different information. So at that time, I had been working on Mavlink, so I would say, why not doing something similar to ROS? And the idea is to be able to translate ROS messages into kind of serialized messages, and then you can exchange them between ground station or other servers. So that was the idea initially. And this led us actually to design a generic architecture as follows. So this is the Dronemap architecture, and our Dronemap Planner was published last year in Ad Hoc Network. It's, the paper is a service-oriented cloud robotic-based management system for the Internet of Drones. So initially we started to work on the Internet of Drones, but then it was generalized to even include any kind of ROS-enabled robot, as I will show in the demonstrations. So the idea here is that we will have unmanned systems, and for every unmanned system you have hardware, and then you have ROS abstraction layers that will make some abstraction to the hardware, and then you will develop your applications. And now we would like to develop some kind of cloud interfaces and web services interfaces here between ROS and the application, so that they will be able to communicate through the internet with remote clients, which could be implemented using mobile technologies or web technologies. So here you have the application protocol, and then you can implement different UAV interfaces or cloud interfaces or web services interfaces to interact with the cloud. So the cloud here will be kind of proxy between the unmanned system and the client applications. And inside the cloud, you can do anything you want. You can do storage, you can do processing, you can do, for example, collect status about your drones, your robots, your unmanned systems, or your users, because in the cloud you have huge infrastructure. So it will allow you to develop a complete managed system. You can use, for example, big data analytic tools to process the information coming. So if we are able to connect these unmanned systems and the client applications through the cloud, then we can do a lot of things. And this was actually the idea. So we start to develop these kind of software abstraction layers to do the connection between end users and unmanned systems through the cloud. So the objective was the following, is to develop an ecosystem for the Internet of Drones and Robots that will allow to connect drones and robots to the internet, will allow users to access them virtually, and to allow also to make computation offloading, for example, for deep learning application. And the system that we have developed, it supports the two protocols, the Mavlink protocol and the ROS-Link protocol. Okay, now the Dronemap Planner started with the Mavlink protocol, and then we have extended it to the ROS-Link protocol, which is the protocol I'm going to explain today. So what is the issue of ROS? ROS is actually a single robot system. If you have, for example, a Turtlebot 2 robot, okay, you will run a ROS core here, and you can access it using one user. Or you can have a drone here, it must have its own ROS core, and you can access it with a couple of users. So every robot is supposed to have its own ROS core. Okay, and this actually will limit. Now, if we want these two robots to communicate with each other, okay, this maybe cannot be done natively by ROS. So you need to develop your software interfaces or network interfaces to do that. And there are several contributed packages, as already mentioned. One of them is ROS Bridge, and some other as well in the literature. So another technique would be to make one central ROS master, okay, and to connect to it all the robots. That's possible. That will allow you to communicate simultaneously with different robots, because every robot is going to have its own topics. So the topic can have a prefix of the name of the robot, but this is very difficult to configure, and it's not scalable. Okay, and maybe it will be confined to only local network. If it is used on the internet, it can be more challenging to do. Especially ROS, actually, it runs so many processes and so many applications. So it's going to be pretty much difficult to maintain such a system, especially if you have large number of robots. So this is why we got the idea of the ROS link. And the idea here is that you have, every robot will have its own ROS interface. And okay, and then we're going to build, you have the ROS master, and we are going to build a ROS link bridge. So this ROS link bridge is going to actually bridge between the ROS ecosystem and the internet and the cloud. And it contains different software APIs that will allow actually to make the communication between the robot and the cloud. So all the robot will communicate with the cloud. We can see this is like a, I cannot say it's a cloud ROS core, but it's cloud proxy that is going to collect all the data from the robots. It can register them, and then we'll connect them to particular users. Every robot will have its own ID on the cloud. Okay, it's even the users will have their own ID, and then this cloud is going to link and relate the users with their corresponding robots over the internet in a very scalable manner. Okay, so scalability here is very important. Also, real-time guarantees, quality of service, all of these has to be considered and taken into account. And this is now the overall architecture. Basically, if we look at the unmanned system, you have the robot hardware and you have the ROS ecosystem, and here you will build the ROS link bridge. I'm going to show you the implementation of ROS link bridge and then a demonstration how it works. Then at the client side, of course, you have your own application, and you need to have also ROS link client. So you have a ROS link client on the user side, and the ROS link bridge, which is also a client. So the difference between the ROS bridge and the ROS link bridge, here it acts as a client to the ROS link proxy. And the ROS link proxy, this is the server. It must be placed on the internet. It must be placed on a public server. So everybody knows about its public IP address, and it has well-defined software APIs like REST web services, SOAP web services, or WebSockets protocols, UDP. You can communicate using different techniques here. And this client is going to communicate with the server. This other client is going to communicate with the ROS link proxy server. And finally, all the stuff will be done here. Okay, so this is the overall architecture. And we have designed a message structure for the ROS link. So every ROS link message structure has a ROS link version. And it will tell about which ROS version the robot is using. It will have its system, every robot will have a unique system ID, and the message will have a unique message ID. For example, this is a heartbeat message, or a message for the motion, or a message carrying out an image. So this message ID will be able to parse correctly the payload. If the message ID is for an image, we are going to parse the payload as an image. If the message ID contains motion information, we are going to parse the payload to extract the motion information, and so on. And here you have a key, security key for the robot, and the sequence number. Sequence number to count how many messages has been sent. Okay, so let me start with some demonstrations that we did using the ROS link protocol and Dronemap cloud server. This is a demonstration that we did for Huawei in the inauguration of the 5G lab of STC, the National Telecommunication Company in Saudi Arabia. And here you can see that we are able to teleoperate a robot, and I will do again this demonstration now, just in a while. And you can see while the robot is moving, we are able actually to see the current location of the robot on the map. We are able also to see the video stream coming from the robot. And you can see we are able, if we have 5G communication, 20 frames per second, okay, which give you real-time video streaming over the internet. And I will show how we did this implementation now. Okay, so you can send the goal location. You can also use joystick to teleoperate the robot remotely. And of course, the most important thing is that you need to have a good internet connection. This is another demo that we did for the computation offloading. This is the first successful demo about making computation offloading from a drone. This is a drone that we control with our ROS-Link and Dronemap system. And as you can see here, this is the environment where the drone is flying, and it is sending through a 4G network the video stream and all its information to a GPU server. So the GPU server is going to detect in real time all the objects. And here we have used YOLO object detector with pre-trained COCO dataset. And as you can see, it's possible to use this for example, the real-time object detection from UAVs or from robots as well. Okay, so this object detection is made in real time. Of course, here we have used the Raspberry Pi camera. That's why the image is not very clear, and because also 4G connection doesn't provide too much bandwidth for the upload. But still, as a proof of concept, it shows the validity of the approach here. Okay, and you can use any kind of pre-trained network for any kind of object that you would like to detect. Okay, and of course, with the 5G connection, we can have up to 20 frames per second, as already mentioned in the previous demonstration. So now let me finalize my presentation with showing the implementation tips of ROS-Link, and then I will take you to a live demonstration. So ROS-Link Bridge is written in Python in ROS. And basically, it is a class that we write for every robot. So for example, this is a ROS-Link Bridge that we developed for TurtleBot 3 robot, but basically, it's almost very minimal change if you consider any other robot, because you are going to deal with the topics. The things that you need to change is the name of the topic in every robot. So usually we start by initializing some parameters. I will take you through all these different methods, and we will start our publishers, because what will do ROS-Link Bridge, when it receives velocity command, it will publish, and it will also subscribe to some topics. For example, it will subscribe to the velocity topic, or it will subscribe to the position topic and send them through web interfaces to the end user to tell about the position of the robot on a map, for example, or it can subscribe to the image stream, so it will broadcast the images or the video to the end user. And we have different servers, WebSocket server and UDP server that we use. And we have different message threads. So here we have different type of messages. For example, you have a message for heartbeat. And heartbeat messages are typically used for telling about the presence of the robot in a system. Okay, usually every second, we send a hello message, or usually we call it heartbeat message every second, to tell the cloud that this robot is alive. If the cloud does not receive the heartbeat message, for example, after 3-4 seconds, it will consider that the robot is disconnected. So this is one way to know that the robot is actually connected to the system, through hello messages or heartbeat messages. So we have different type of messages I'm going to explain, and also command messages that come from the client. Usually command messages, they come from the user. For example, the user sent a twist message to make the robot move. It will be received by the ROS-Link Bridge, and then will be published to the ROS ecosystem to make the robot move. So let's first look at our ROS publishers and subscribers. First of all, we need to create the publishers for the topic of interest. So now if we want to make the robot move, we need to define a publisher for the twist message. Okay, and here you need to specify correctly the velocity topic. And this will depend from one robot. It's basically /turtlebot/cmdvel in ROS, or could be something else. Okay, but here, this is the publisher that you will use, the ROS-Link Bridge will use if it wants to make a robot move. And also we have subscribers. Now here we are going to subscribe to only 2 topics, but you can subscribe to any other topics. We are going to subscribe to the AMCL pose. And this is the pose that we need from the robot navigation. And we will subscribe to the compressed image. So every image that is received by the robot, for example, collected from its camera, it will be captured by the subscriber, and then the ROS link bridge can send it to the user through the cloud. These are our publishers and our subscribers. And then we need to initialize our servers. So what does it do, the ROS link bridge? It will send the messages through UDP or WebSocket interfaces. So here, for increased reliability, we define two different servers. We define the UDP, we have in the cloud, in the cloud, we have UDP server and the WebSocket server. So we will connect to the cloud using a UDP client and a WebSocket client. So two clients will be used. For example, if the UDP client fails, we can use the WebSocket. And if the WebSocket fails, we can use the UDP client. This is for increased reliability, but any of these will be sufficient. In the first version of ROS link, we have only used UDP. But later on, we have switched it to WebSockets because it is more reliable, in particular if we want to submit real-time video streams. Okay, so we found that WebSockets are more suited, in addition to some other difficulties for implementing streaming with UDP as well. So here you can see in the parameter initialization, we are going to take the IP address of the ground station. By default, maybe it's the local address, but basically we will take it from a launch file. And here we can see the IP of the server to which it will connect. And then we start the WebSocket client in the ROS link bridge. And this one is going to connect to the WebSocket server that is in the cloud. And the cloud now we have hosted our cloud system into DreamHost, Dream Compute instance, and it has a public IP address. So what we do here, we specify the web service protocol. This is the IP address of the instance. And here we are going to use the WebSocket, and we have to specify the user ID because every user is allowed to use his own robots. Okay, so we make user management. So you must know what is your user ID and the robot ID. This is already also implemented in the client interface, as you will see. And then, of course, you will open the WebSocket communication with the client. And of course, you will handle messages that will come. You will handle errors. You will handle the closing of the WebSocket and the opening of the WebSocket. So here for increased fault tolerance, what we did, if the WebSocket closed, because now when you work on the internet, maybe sometimes you have dropped connections. Okay, so the WebSocket is going to close. In this case, we are going to restart it after a certain time. And this will make sure to always connect to the web server, to the WebSocket server, as long as the WebSocket server is alive. Even if the connection drops, it will reconnect again. And here you can see in the WebSocket, we have an event on message. So if there is a message that is received from the client, in this case, you have to process it as a command because the client will send command messages, process, ROS link, command, message, and here you provide the message information. So we will see what we will do here in the process, ROS link, command, message. Now let's look at the message threads that I have talked about. We have several messages, and the messages are those sent from the ROS link bridge on the robot to the end user. For example, I want to tell the user that the robot is alive. So in this case, I have to send a heartbeat message, which is a hello message sent every certain amount of time. So here we specify an attribute, heartbeat message rate. For example, you want to send 1 message per second, or 2 messages per second, or 10 messages per second. This is something that you can configure into a launch file. And here you will send through the client socket, and we will send to, the heartbeat is sent both on the UDP interface and on the WebSocket interface, because this is an important message. And you specify the server address, and you specify the type of the message. It's ROS link message heartbeat, and which thread is going to execute it. So same thing here, we can send status of the robot, we can send the global motion, which contains the XY coordinate of the robot, the velocity, as you will see later. And you can see an image as well. So for every type of message, we have a particular thread. So this is a multi-threaded system. And in this case, no thread is going actually to preempt the other, or no thread will have to wait for the other. Everything is executed in parallel. And this provides better scalability. You can add more messages. You just need to add them into other threads. And the commands also operate on a different thread. So when a command comes from the end user, it will be executed through another thread. Let's look at the heartbeat message. So now, when you say, I will send a heartbeat message like this, okay, so basically every message contains a header and a payload. So this header is common to all messages. It's common to all messages. And it has the type ROS link message header, heartbeat. And here the payload will contain the information relevant for the hello message, which is the message header that is defined above, the type of the robot name, the state of the robot. Now here we will say that the robot is active, the owner ID, and the operation mode. These are some general information that we send to the cloud every 1 second to tell the cloud that this robot is alive. And maybe if it is crashing, we can change the state of the robot. For example, we can make robot state crash. It's another number. So we have here predefined numbers for every state of the robot. We have also the global messages. Okay, and this is the motion message. Now, we collect the information about the motion from either AMCL pose or the odometry pose. Okay, so we will collect X, Y, Z. And we collect, so here we don't collect the Z because it's a ground robot. So only we need X and Y. But for a drone, we are going to collect Z as well. We will take the information of the linear velocity, angular velocity, and the orientation of the robot, pitch, roll, and yaw. So all this information, from where they are collected? They are collected from ROS. How to collect these messages? Using pose callbacks. So we have a callback for AMCL pose, and we have callback of odometry pose. So you can choose if you want to take the position from AMCL pose, or if you want to take the position from odometry pose, you can choose which callback you want to activate. And here, what does it do? The callback, it is going just to update the state variables. We have ROS link state variables will be updated every time, so that when you send a new motion, it will send the latest value of the state variables. So these values are continuously updated by the callback threads. Okay, and you can choose which thread you would like to use to update your position. It can be AMCL or it can be odometry. And here, for example, another message for sending an image. And here sending images is more complicated because you have to serialize the image. Okay, so same thing here, we have a header and you have the payload, and the payload will contain the image itself, the data, the height of the image and the width of the image, and some other information about the user. So this is the callback of the image. Whenever there is an image published on a ROS topic, okay, it will be processed by this callback. First of all, we extract the image from ROS and we convert it to OpenCV format. Then using OpenCV, we are going to decode it. We will resize, encode the frame into GPG, then encode it into base 64, which is the common standard to serialize messages into network messages, or serialize images into network messages. And finally, we will update the state variable of the ROS link image data. And this will be sent through this method. Okay, so this in what concerns state information. So state information, they are collected from ROS and sent from the ROS link bridge to the end user. And now the second category are commands. So we can receive, and the commands, they are messages received from the user to the robot. So now when a user sends a command through a mobile interface or a web interface, it will be received by the ROS link bridge. And let me take you to this method. This one, okay? When a message is received on the WebSocket, it will be processed. Process ROS link command message. So here what we will do when we receive a message, first of all, we are going to extract the command from the JSON message received because here the information is serialized in JSON. And then we will check what is the message ID. For example, if the message ID is for a twist command, it means that the user have sent a twist message, which is a linear velocity and angular velocity. So we will collect this information from the command received, okay? And this information will be then published to ROS. This information will be published to ROS and will make the robot move. If you update this linear X, linear Y, linear Z, and angular X, angular Y, and angular Z, if you update them from the command received by the user, these new velocities will be published, and of course, the robot will be moving. When you want to stop the robot, you can send 0 values, and the robot will stop. Another type of message is, for example, receiving the map. You want to make map-based navigation, so you want to receive the map on the mobile interface. So you can send a map command, and here it will access the map into the map location. It will be stored locally in the robot and will be converted into JPEG format, and finally encoded into base64 and sent back to the user. And 2 other commands, for example, the user has sent a goal location. You want the robot to autonomously navigate to a goal location. So in this case, we will receive the X and Y coordinate from the mobile interface. And finally, we will invoke a thread that is called move to goal. And here, simply, it will just call the move base action leap by inputting the values of X and Y to the action leap, and then the robot is going to move. And you can also send an emergency stop by putting all the velocities to 0. Okay, emergency stop, for example, if the robot is going to crash or something, you can send an emergency stop. Okay, so this is now the end of the presentation, and I'm going to start a demonstration on this. Okay, so let me move now to my ROS virtual machine. Are you seeing my virtual machine now?
Yes, we can see it.
Okay, so before going to the virtual machine, let me take you to the, this is the web interface, which also work on mobile as well. So we have, because we developed this application in Ionic. And with Ionic, you can generate Android application or iOS application or web application. So you can see now I am logged into the system, because here, if I log out, so you cannot see anything. You cannot use the page only if you log in. So I'm logging into the system. It recognizes me as with my name, and I have my owner ID is 12. And you can see now I don't have any robot. There is no robot connected over here. And look, now this is connected through the internet. So not even on my local machine. This is located in some server over the internet that will allow me to control my robot that is located into my virtual machine. Let me first show you here the structure. So what I have presented to you is this file, okay, which is the ROS link bridge for a TurtleBot 3 using WebSocket. And we have a configuration file that is the TurtleBot 3 roslink.launch. And here we configure some information. For example, I will send the heartbeat message 2 messages per second. The robot statue message will be sent 2 messages. So you have the ability to choose the frequency of sending different messages to the cloud. And here you can specify your owner ID. So in order for me to be able to see the robot, I have to make sure that my owner ID is the same as it is shown here in the interface, which is 12. And here I have a robot with a certain system ID 13, okay? And this is the name of my robot, Anis TB3. So now I'm going to start my robot. First of all, I'm going to start Turtlebot 3. Okay, I think that all of you are familiar with Turtlebot 3 simulator. This is running on my virtual machine. And I will start the navigation of Turtlebot 3. I use some acronyms, but this is actually the ROS launch Turtlebot 3 navigation. Turtlebot 3 navigation. I have some just quick shortcuts. Okay, and this is the RVs that everybody knows. Okay, now we can see this is our robot now. Now this robot is not connected to the cloud. Okay, so far it is not connected to the cloud. And I'm going to add another video broadcaster. So this is just to emulate that this robot is sending video information. I have developed here a small script that is actually showing the video capture. Or what I can do, I can run the stream of my camera. Okay, I can run the stream of my camera, and here I will specify. So if you look, if you make ROS topic list. Okay, so now we have this stream that is generated from my USB camera. I'm going to subscribe to this stream in the ROS link bridge. So I'm going to subscribe to this stream as the camera topic. So look, I will change the camera topic to be this one. And now I have everything ready to start my ROS link. Okay, let me start the ROS link bridge of Turtlebot 3, which is actually, if I run the command, it's ROS link, ROS launch, ROS link version BA, and then TB3 ROS link launch. So I'm going to start it. Okay, so now ROS link has started to communicate with the cloud. And now if I refresh my page, okay, I can see my robot, which is Anis TB3, the same that I have started from my virtual machine. And of course, this is through the internet. Okay, through the internet. So I can now open the stream, and you can see this is the stream coming from real time. And I can switch here the position of the robot. You can see this is the current position of the robot, which is the same that is shown on the map. Okay, let me now make the robot move to this location. So I send a goal location here, and you can see the robot is currently moving. Okay, it's currently moving, and it is moving here as well in the simulator. Okay, in the same way. Okay, so I can make an e-stop to make the robot stop if I want. And now, for example, I can teleoperate the robot like this. Okay, so you can teleoperate the robot, and basically anyone now, if anyone register in our system, I can give him even the possibility to teleoperate this robot that is on my machine. Okay, so if anyone would like to try, you can for example go to the system here,
Yeah, I would like to try.
Yes, no problem. So in this case, everyone can try to register, okay? And then we can give him control. I can restart my Turtlebot 3 to give him control from there. Okay. I can show you also another demonstration with the real robot. I have a real robot here on, so I can show this. My camera now. This is a robot in my office. You see it?
No, sir.
Let me check my camera first. Okay. Connect to Mac. Okay, yeah, because I have removed the background. Yes. Hello? Okay.
Yeah, it's fine.
Let me remove the background from my virtual background. I have to remove it. No. Okay. Okay, so I have a robot here. Okay, so even if anyone would like to remove the robot, that's possible. I just need to take, we can make a demo, you know, if anyone registers to the system and log in, he can send me his, if anyone registered to the system, he can give me his ID, and I will configure this robot, this real robot, to be controlled from wherever he is. Okay, I'm going to start. Anyone would like to move the robot?
Yes, I register.
You have registered, doctor. So Dr. Ibrahim is in Norway.
Yes.
I'm in Saudi Arabia, so you'll be able to operate my robot here.
Yeah.
Just give me your ID.
Yes, just a minute.
Okay, so let me go to.
It's just email and password.
Yes, after that you have to log in and give me here. It will tell your owner ID is, and you give me the owner ID.
Okay.
Okay, SRC. So what I will do now, I will just change the user ID. And it will be good, Dr. Ibrahim, if you switch to your screen so that we can see you teleoperating with the robot.
My ID is 19.
19.
Yes.
Okay.
So there is no robot connected to the server that you have?
Yeah, there is no robot connected now. I will connect to this robot to you. And the problem, this robot is running on Raspberry Pi. Some things look, I try even to update. Raspberry Pi sometimes disconnects. Okay, now I have updated this one. Control X. Your order ID is 90.
Yes, 19.
Okay, can you now switch to your screen?
Okay, and I need to log in first?
Yes, you need to log in and switch to your screen so that everyone can see your screen.
Okay. Your connection to the site is not secured. I should site setting or what?
No problem, it's...
Dr. Ibrahim, if you just registered, you will be logged in by default.
Okay.
Can you turn on your screen just that we can see whether you are logged in or not?
Okay, so I will just share my screen.
Yes.
Yes, yes.
Okay. Yes. Can you see my screen now?
Yes.
Okay. Okay. Now you don't have any robot. You see? Okay. Now let me start the robot here.
Yes.
Just a moment. No, you don't have any robot. I will start it now.
Okay.
You will see it in maybe 20 seconds.
Okay.
Just at the time it connects to the cloud, and when I tell you to refresh, you can refresh.
I cannot see.
No, it's still starting. It's still starting. You know, Raspberry Pi is slow, so it will take 20 seconds to start. Not like on my virtual machine, it's fast. Okay, doctor, try to refresh now.
Okay. Yes, now I am in.
Yes, you can see real TurtleBot 3.
Yes.
Click on the image,
Okay. Yes, and I can see you. Yes, and I can see the map. Yes.
Try to move with the joystick now. Try to move with the joystick. Okay.
It's just directions.
Yeah. No, start from the middle and push on to the top.
Okay.
It's moving. Are you seeing it's moving? Make it to the top. Now
Top.
this is right.
Okay. Connection is lost.
But it is moving. Are you seeing that it is moving?
Yes.
Yeah, sometimes because the Raspberry Pi, the connection with the Raspberry Pi is not very much like it's showing, you know. But if you press from the middle to the top, it will move forward.
Okay, like this.
And it is moving this. Okay.
It hits the wall.
Yeah. You can stop it now.
Yeah, I can hear it.
To the crash.
Okay, stop.
You can make an e-stop.
Yes.
Okay, now it's
Okay.
yes.
Does it crash the wall?
No, it doesn't. No, it doesn't crash.
Okay.
Yeah, so this is just a demonstration about the process. Okay.
I think it's very exciting and lots of application, not only in robotics, in fact.
Yeah, it can be used with any kind of unmanned system using ROS. I can show you now something, just a few performance tips. Maybe I can switch to my.
Okay, I will stop sharing my screen.
Let me share my screen again. Come back to my microphone. So, of course, the system to be successful, it must be used with very good internet connection. So, if I use back again this robot. Okay, so let me show you, for example, if you have an image coming from the drone, let me stop this TurtleBot 3. And I will change the topic. to a video that we have collected from the drone. So here, let's run. ROS link. Okay, I'm going to broadcast a video, and this video we have collected from a drone. Okay. I don't know, my system is a bit slow. Let me try to remove this one. Try to make it a little bit faster. Okay.
It's a very, very beautiful campus.
This is our campus in Prince Sultan University. Yeah. And now I'm going to start the robot again. Okay. And you will see, for example, this is just to emulate images. This is collected from DJI drone. And we can actually see the images. Let me restart again. I have to make sure about the topic. Yes, maybe I did not save. It's UAV video frame compressed. Yes. Let me stop this one. Oh, yeah. I understand why. I have to make a ROS launch, ROS core again. ROS core. And then the broadcaster. And then TB3. Okay, so you can see now, you can, for example, imagine that you have a drone with ROS, and you can have high quality images. So here I'm sending only 1 frame per second. Of course, if you have high resolution like this, you cannot send in several frames per second. But one of the things that you can do here in the video broadcaster, you can reduce the size of the image. So for example, here I can make a compression to send only half of the image. Okay, so in this case, you can have lower communication quality, but you can increase the frame rate. Look now, you can decrease the quality, and in this case, you can send more frames per second. And if I want to send more frames per second, I have to modify this parameter. So now let me send, for example, 5 frames per second. You can restart Turtlebot 3. Now it has stopped. And you can see now I have been receiving almost 1 frame per second, 0.85. Now I have updated this launch file with 5 frames per second. And you can restart again. So it is starting now. Let me reset the connection. Okay, so we have larger number of course, you need to have sufficient bandwidth. Now, the upload bandwidth, you can see now it's more more smooth. The upload bandwidth that I have is 5 megabit per second, but of course, if you have more, you can submit at higher resolution and higher bandwidth as well. Okay, so you can see it's almost coming in real time from the images here to here. And here you can also add some additional layer if you want to use a computer vision applications to detect cars, to detect people, to detect any particular event. So you can send these images to the cloud, and then from the cloud, you can make GPU processing, and finally, you can send the events to the end user through the interface. So I would like to take the opportunity to make big thanks to my research engineers, Mahmoud Al-Ahdab and Anas Kanhosh, who have been working really very hard to make this software, the Dronemap Planner client application, and also the ROS link bridge. And especially Anas in the last days have been working very hard to make all this demo up and running. It has been running, but we had to do a lot of changes for for today's presentation. So by the end, I reached the end of my presentation, and I will be glad to hear from you if you have any questions.
Thank you very much, Professor Anis, for the great presentation today. So please just unmute any questions if you have any question. So if anyone has questions, just please unmute your mic and ask your questions, and Professor Anis will answer you.
Yes, Dr. Ibrahim, this is Mohammed Saqib from Jeju National University, South Korea.
Hello.
Hello. Yes, Dr. Ibrahim, this is Mohammed Saqib.
Yes, Mohammed.
Yes, Mohammed Saqib. I have a question that as Professor said, that we are using cellular communication like 3G, 4G module. So in cellular communication case, the IP not remain static, I think so. So how the dynamic IP has been handled, like in case of transmission from the drone to the ground station, we just define the static IP on the drone. So it just send this transmission to the static IP to the ground station. And in case of ground station to drone communication, so how the communication will be handled, like the IP of the drone will be changed with the passage of time. So how this we can handle this?
Yes, so let me clarify now. You have this figure here. So, okay, your user can be on 3G, 4G, your drone can be on 3G, 4G, okay, doesn't matter. So here we have unknown IP address, okay? And here you have an unknown IP address. And that's actually the idea. And here you have a known IP address. So there is something that probably I didn't show today is the server side. Okay, and this is actually the implementation of the server itself, which has been in Java. Okay, the cloud manager, and this one is located in a known in a server on the cloud with a known IP address. Okay, yes. So now if I have a drone, what does it do? It will connect to this known IP address, and then this one is going to identify this drone, which is the temporary IP address, because now when you connect, you will be identified with a temporary IP address. Same thing for the user. Okay, when you open a WebSocket connection, halas, it is opened now. And here you open a WebSocket connection, it is opened. So it doesn't matter that, and this is the difference between a ROS bridge, where the server was located in the robot. So in this case, your question makes sense, because I don't have the IP address of the robot. How can I connect to it? But now what we did, we didn't put the server into the robot, but we did put the server into the cloud. And the cloud,
yes, of course,
by definition, will have a known IP address. I hope that I have addressed your question.
Yes, thank you, Professor. And one thing more that in cellular communication, we also have some kind of coverage restriction.
Yes.
So the satellite communication can also be leveraged with this in the future, I think so, for
Yes,
the out of coverage communication.
basically, this is agnostic to the communication layer. I mean, you can use it with any communication protocol, satellite, ZigBee, or 5G, 4G. We have tried it with 4G, with 5G, with just here local, optical fiber networks. So as long as you have IP connectivity, you can do the job.
Okay, thank you.
Either through satellites or any other kind of technology.
So this ROS link bridge code is open source. It is available on GitHub.
Yeah, let's say yes. I will make it open source. So for the ROS link bridge, we will make it open source quite soon. The only thing is why I didn't put it so far, because for the moment it is related to the Dronemap Planner, which I'm not really. I don't have plans to make it open source for the moment, probably in the future. But I would like to release it with some kind of small open source proxy that will be in Python, so that people can do the same experiments without having this big cloud server that we developed. But we will release it soon, inshallah, the ROS link bridge. There is no closed source for in what concerns ROS link, and it can be extended easily.
Okay, thank you, Professor.
Yes.
Hi, Mr. Anis. I'm Debashish Das here.
Yes.
I just wanted to ask the robot side, do we have a offline caching mechanism in that, the code written on the ROS robot side? Because if the connection fails, then by that time, whatever data is being generated from the robot or the sensors, it needs to be caching locally, and then later it should sync to the server.
No, we didn't do any kind of caching, but here in ROS, you have already, in the publisher and subscribers, you have a queue message. And the queue message is going to store some kind of the latest messages, okay, before being deleted. So this is the only thing that it's handled only purely by ROS, but we didn't implement any specific caching messages. And of course, as already mentioned, the success of this application is based on having a very good communication quality. We cannot guarantee the use of unmanned system through the internet just by any best effort communication quality. And this is the real future, will be with the start of 5G networks, where the latency is very low and the reliability is very high. But now with the 4G network, it's still affordable, I would say. It's okay, but it's not something that will be like very, very reliable, because we did experiment with 4G and we know what kind of the limitations. And with 5G, things were pretty much smooth and very much reliable.
So currently, you have not used the server for any kind of computational processing, or the whole navigation stack is not running on the server side, but it is still at the robot side, but the data can be fetched for visualization or giving some commands on this side.
Yeah. Everything is running in ROS in the robot side. Okay, so the ROS link is like an intermediate. It will take information from ROS, send it through the cloud to the client. For example, it will take information about the velocity. It will take information about the position. It will take information about the map, pack them into a message, send them in real time to the user.
Thank you, sir.
Yeah.
Hello. Hello.
Yes.
Hello, Professor Anis. I'm Sulaiman from Iraq. I want to ask you about the possibility to share the control of a single robot among more than a single user. Are the ROS link is able to share the ID of the single robot among more than user at the same time?
Yes, we have actually we have developed a version. Actually, it can work basically on a server like this, or even on a single user, single robot. This is possible. And we will be releasing actually the code for communicating with ROS link with one user and one single robot, and then it can be extended by the developer in the way he wants.
Yeah, okay, thank you.
Yeah.
Hello, I have a question. If can you hear me?
Yes.
For example, if I make a VPN server and I make the bridge with that server, and
Yes.
I use with the multi-machine of ROS.
Yes.
What is the difference between what you did?
If you make VPN, you can do it. You can do with ROS bridge. That's possible. But you know, VPN, you depend on a third party. It's not your own solution. Okay. And here, in addition to ROS bridge that will make virtual access, okay, here in ROS link you will be able even to make computation offloading, because you will be able even to extract images in real time, process them on the cloud, and send the result back. Okay.
Yes, right.
So yeah, for me, when I wanted to develop my system, I didn't want to be dependent on any third party. It's a proprietary system that anyone he can use it for his in a proper way. Okay. Because now if you take a VPN, you know, you depend on someone else. Okay.
Okay. Okay. Thank you. Thank you.
Yeah.
Great job.
Hello.
Hello. Yes.
Yeah. Hi, sir. Thank you for your presentation. Actually, right now I'm using the same system. I have a Raspberry Pi with on the other side, and I'm controlling with the cloud. But I'm using Google Cloud right now. And
yes.
The thing is that with the Google Cloud, I have to take each and every message data and publish it differently. Like I can't publish the whole message together of the whole ROS message together. So I think this technology is very feasible for me. So I want I want to have I would like to have the code for this. As soon can you provide us for that?
Sure. We will try to release maybe within next 2 days the ROS link bridge. And by the way, the ROS link bridge is independent even from our server. I mean, even you can connect it with Google Cloud or with Amazon Cloud or with any other cloud that has WebSocket interfaces. You see what I mean? Okay, because here, look, here, what you can modify the way how the servers are created. I can tell you. So now, for example, we are using a WebSocket here to connect to our server here, WebSocket. So you can even change this code to connect just to Google Cloud and sending the same messages. Okay, so all the same messages will be sent to Google Cloud or to Amazon Cloud, and you can choose whether you want to use REST API or WebSocket API or SOAP API or any other API. Because here, ROS link, basically, it's a complete ecosystem. It defines standard messages. Look, I will show you here some more details about the code. What is ROS link? This is SRC, yeah. So here, for example, we have standard messages of the code. We have predefined types. We have predefined messages. I'm not sure where are the messages here. I'm not able to locate them. Yes, messages here. So you can use these messages, which are already serialized in JSON, which has already taken updated information from ROS and send them to any cloud server that you want. So it's really flexible. All you need to change are the server interfaces here. Okay, this part.
Okay.
And you can reuse all the other part. Yes. For us, what we will provide, we will provide a small server in WebSocket that will allow you to have the whole loop. And then as a developer, you can change this server in the way you want, okay, to connect to your proper interfaces.
Okay, so any of the cloud using WebSocket, sir, we can use this whole code and we can control the robot.
Absolutely, absolutely. All you need to change is here. And in your server side, you just need to know what are the JSON messages received. Of course, you can debug the JSON messages,
Yeah,
JSON messages. Yeah, decoded, and then you extract them on the cloud in the way you want.
Correct, correct. Thank you so much. Thank you so much for your presentation.
Yes.
Hi, Dr. Anis. Just wanted to ask another question. That you have mentioned
Yeah.
that you are sending the map file and also the AMCL post data. So the map file you are sending just as an image, and AMCL is a post data that is being sent here. So can you explain a little bit in detail? So image means is just a JPG file, or it's a whole back file that is coming out here? So can you explain a little bit also in the AMCL part, all the only coordinates are coming, or orientation and a lot of other things are coming out?
Yeah. So what we do here, of course, when we say that you have images, these images are going to be taken from a certain topic. Okay. So now in my demonstration, I did with taking images from USB camera or from a video clip recorded. But for ROS link breed, it doesn't matter. What matters is what is the topic you would like to use for the camera. Okay. So now for your proper robot, you need to first identify what is the topic that has compressed frames. And here we work with compressed. It doesn't work with raw because the transport layer for compressed messages, for compressed images is different from raw images in ROS. And here for transmission, it's better. Let me explain, yes. And then what you will do, you will define your subscribers, okay?
No, sorry to interrupt you. I was asking that the map is coming as an image file.
Yes.
So,
yes, the map is located here. Look, we have the map. It's located as a JPG format, right?
So the whole back file is not coming.
No, not the whole back file. We sent only this image. We sent only
and this is encoded with the OpenCV library and sent as an image frame as the camera image frames are coming.
Yes.
And can you explain a little bit on that AMCL part? What are the data that are coming as an AMCL post data, or is the whole package is coming? How?
Yes, for AMCL, let me go to AMCL here. Okay, so AMCL is going to update. You can take this position, AMCL position from ROS. Okay, and what we do, we will update our state variables. So these state variables are global variables defined in Python, accessible for any method. Okay, so then when we send these state variables when we send these state variables about X and Y, we will send the latest values collected from the AMCL post. Okay, we will submit them here. This is the callback. We have a global message here. Look, this one is going to send to the client the latest value collected from ROS about the position of the robot. It will be sent into a global motion message. So here you will put the X value, the X coordinate, and also the Y coordinate, and also the yaw, and all other information needed. Vx, linear velocity, in the X-axis, in the Y-axis, in the Z-axis, and here you have the angular velocities, and then you have the pitch, roll, and yaw. Because why we put all this information? Because this is also applicable to drones, and drones, they work on 3-dimensional space. So we keep updating, and of course with drones, we are not going to use AMCL pose because there is no map-based navigation for drones, but we will update using, for example, GPS location. Okay, so it depends on the robot. It depends on which topic is responsible for providing you the global location information of the robot. Does it make sense to you?
Sure, thank you so much. I understood.
Okay. Any other question? Okay, thank you very much.
Thanks a lot, Dr. Anis, for the great presentation today. Lots of information, lots of knowledge today, in fact. and we had lots of audience from around the world. We had more than 70 at some point, which is really very good. So I'm so appreciated for your presentation today, and I thank all people who joined us today. And please join us for, I mean, in the future, we will try also to arrange more webinars. And thanks a lot for joining us today. Yeah.
Okay, thank you very much. Have a nice day.
Thank you, Dr. Anis. Thank you very much, and happy Ramadan to you.
الله يبارك فيك.
شكرا جزيلا. جزاكم الله خير.
الله يبارك فيك.
حاجة رائعة، جميل جدا والله. شكرا جزيلا.
الله يبارك فيك. الله يبارك فيك دكتور. جزاك الله خير. شكرا.
Thank you, Dr. Anis.
Thank you very much. Thank you. Thank you. See you next time.
Thank you.
So the video will be uploaded to YouTube, and I will share YouTube video with all of you.
Thank you.
Thanks a lot.